Back, good to see all you guys. I guess it's been a week since I saw you. We, as you know, I had done a lot of work on Tuesday. Obviously Thursday was no class time. You were hopefully enjoying some turkey and Thanksgiving and all that good stuff, and then quickly ate that and did all your homework and are all caught up and are all refreshed and ready to hit these next 2 weeks really hard, because I know these 2 weeks can be really hard. So the better you can come in ahead, the better you are. If not, oh well, that's where you are now, and so 2 weeks. And so if I lay out the schedule here of 2 weeks, obviously we've got today, we've got next Thursday, we've got next Tuesday, and then the following Thursday after that is the exam. So that's a short way of saying is we have only 3 lectures left and quite a bit of material to cover. We'll see how far we get. Hopefully it will suffice, and I think it will. I wish there was more time, but that's just the way it seems to always fall out. Not just this semester, but it seems like every semester. There's just a lot of material. How come my overhead didn't go on? I gotta do that. All right. Anyways, I just wanted to say here is when I saw you last on Tuesday, as you might recall, we got into chapter 32, and so what I'd like to do today is to finish up chapter 32 and then even jump into chapter 33 if time's allowed. Fortunately, 32 is not a real long one, and neither is 34. 33 is a little bit on the long side, so like I said, we'll see how far we get. A couple other things going on. I got a bunch of things recorded down, and so they're sending around. If you want to take the time to dig through it now, great. If it's after class, fine. If you want to do it in lab, that might even be better still. I'll just pick up all these papers and all these big binders here and put them. So this is the time that I'm trying to catch up on all those papers you've turned in. You guys probably saw the email I sent to you. For those of you who didn't, check your pipeline account. It's got a link to your posted grades. It's got your homeworks recorded up to some level. Got a lot more recorded yesterday. So if you want to look at that, just obviously the next 3 weeks, keep looking at that link and you'll keep seeing more and more things recorded. And especially if you've turned anything later, if you think I'm missing anything, shoot me off an email and then I can double check and then say, okay, well, no, I just haven't got to that, or yes, I have it, I just haven't recorded it, or whatever the case may be, or no, I'm missing it completely, or in a lot of cases, it could be a missing name. I noticed the chapter 28 that I just got recorded this morning. There were 3 missing names, so I just wrote on there no name, and obviously you don't have a score if you didn't put your name on there, but there's quite a few without names on it.
When's the last day to turn in late homework?
Oh, last day, end of the semester, but I mean,
So the Thursday before finals?
Yeah, that Thursday before finals, yeah, so that'll be a good time. Also, a number of you got an evaluation form. Hopefully all of you did, and a number of you already have given it back to me. That's great, but obviously there is more of you out there, so if you still have it with you sometime today, this week, whatever, drop it off. I'm going to carry this with me for the rest of the semester, and so please fill it out. Like I said, it'd be nice to shove in my little binder there, and probably in January I'll dig it out, or since this class is only taught once a year, it might not even be till next summer before I dig it back out. But as I plan on and get ready for the next offering of this class, which is next fall, I'd really like to look through all of these, but so won't have time to look through them between now and the end of the semester, obviously, but I will before I make my syllabus for next fall. Well, all that is to say that we learned for the first time, or maybe I shouldn't say for the first time, but we applied Faraday's Law for the first time in this chapter. It was called Induction. And so let me kind of just start there. I don't want to take too much time repeating what we already did, but I tried to introduce you to chapter 32 before we left to kind of entice you, if you will, and get you ready for an application chapter. And so here's what we did. We said, let's take a power supply some kind of voltage. You might remember last time I had the voltage set at 10 volts. I'll do that again. Here is the power supply set at 10 volts. What would happen if you took that power supply, you ran it through a switch, from the switch you went through, and at first I said just nothing but an ordinary everyday wire. So nothing really spectacular, and then through a resistor. And if you plotted the current as a function of time, defining time equaling 0 of when you close that switch, you would expect to see something to this effect. That 0 current would occur until you close the switch. Once you close the switch, then your current would start up. And the amount of current would be the voltage divided by the resistance. And so that's the kind of thing we learned way back many weeks ago on what would happen if you just had a power supply, a switch, and a resistor. And what we're adding this chapter, and I'll put it right here, is we are going to take and put, maybe I'll put a little core here, and we will put then a wire that is wrapped around a magnetic core. Or we won't even have to do the magnetic core. We haven't done much with the whole idea of the material anyways. As I said, that'll be your next semester as you get into magnetism. But the point here is, what would happen now? What would change? How would this be different? And so maybe I'll change colors. Here's the logic. Here's the experiment that we saw, and I'll run it again, is we saw this. That now, the current, of course, is still 0. And if you close the switch at time equals to 0, something new happens. Something different that didn't happen before. It has to do with Faraday's Law. It's the whole reason we learned Faraday's, well, not the only reason we learned Faraday's Law, but one reason for Faraday's Law was using it in what we call inductors. And so this chapter is just that. It is to introduce you to an electronic device called an inductor. And what's going to happen is this. You can imagine when this switch is closed that the current tries to go through this coil. But what we learned from Faraday's Law was there would be an EMF created. And so this would have an EMF that would be equal to the number of turns times the change in flux in that device. And so, without this device here, which we are now going to call an inductor, I would have had a loop and it looked something like this. The voltage minus IR equals 0. That would have been without that inductor. But now that we are 13 weeks into the semester, we throw in another piece to this puzzle, and it would look something like this. The voltage from the external battery minus N d phi dt minus IR equals 0. And that's the added piece to this equation. And that's what this chapter completely studies. It's why I said it's a fairly short chapter, because it is just taking one application of Faraday's Law and what we call inductance, self-inductance. It is how does the current in the circuit affect the current in the circuit. Why it's called self-inductance. And soon we'll talk about mutual inductance. But for right now, it is self-inductance. How does the current in the circuit affect itself? And that's what we want to know. And so this is that added piece. This is the piece that would happen. And what would happen? Well, let's run through the math here. Let's work this out here and then watch it on the screen again in the same experiment, but now we'll have some numbers to work with. Is you might expect that as the current goes here, and as soon as you close the switch, you are trying to shove current in through this way. using the right-hand rule that we learned a couple chapters ago, I believe it was 30, that this inductor is what we'll call it now. If you still want to call it a solenoid, fine, but when we take a solenoid and apply it directly to a circuit, we call it an inductor. And so as I take my fingers and I curl it, I would say the current coming from this circuit is trying to make flux this way. Then so Lenz's law will tell me that we want to create an EMF and a flux that way. And so that is an electric field pointing in that direction. So I might think of my inductor, my solenoid, as being another battery. And it would now look something like this. This is the voltage from my external source, and this is my voltage from my Faraday's law. And so what we have is competing voltages, if you will. And so what I should get for the current would be something that mathematically looked like this. The voltage minus a voltage that is created from Faraday's law divided by R. And so that would be the equation for the current at any given moment in time. You can see it's going to get kind of complicated here, because how does this voltage, which isn't a constant but determines on the change of the current, and the current depends upon the change of the current, we've got a differential equation that we're going to have to discuss and solve for here in just a second. But the concept is that I would expect then there to still be, the moment I close the switch, to still be zero current, because what's going to happen is the EMF produced by Faraday law is going to be equal to the external battery, which in my case is 10 volts, and so I would have 10 minus 10 and a net voltage of 0, which gives me 0 current. So as soon as I close that switch, I still have 0, but the current is on the rise. How do I know it's on the rise? Well, it's got to be changing. That's what Faraday's law says, right? To get a back EMF, you have to have a changing flux. So the current has to be in the process of increasing. So although the current may be 0 as soon as you close the switch, it can't remain at 0. If it remained at 0, there wouldn't be any changing flux in that solenoid, that inductor. And so what I get is something that, as you saw in the experiment last time, and you'll see here again, and we'll go through the math, is you will see that the current does increase, but it does take some time, if you will. And that is what this inductor does. So let's try to solve it. Let's try to solve this equation. And so I want to focus first on this. I know the equation is a bit more complicated with all the pieces in there, but let's just single this one out, because again, that's what this chapter is about. As I said, probably the good news here is no new physics. There's no new law or rule to learn in electromagnetics. It is, what did we learn in the last chapter? Faraday's law. Let's apply it to our circuits, see what that tells us. And so let me focus closely on this. So I'm going to put the EMF is equal to a negative L d phi dt. Okay, and now take a close look. I'll start with N. This is from the last chapter, but remind me, what's N again? Number of turns in the primary or secondary? Right, that N was the number of turns in the secondary, right? But wait a minute, what is the primary and secondary here? And it's really both the same. And it can get confusing because it is the same. In a lot of sense, I think it's supposed to be easier because there is no secondary and primary. I mean, this is what it is. The primary, as we talked about in the last chapter, is the current. The secondary is the voltage that is produced because of that current change, right? But the number of turns is coming from the same device. In other words, we are saying that the primary is the coil, but also the secondary is the coil, because we are looking at how much voltage is produced in itself. If we had another coil wrapped around it, as we did in the last chapter, then that was called the secondary, and the N was what we called the number of turns in the secondary. We don't need to label them anymore that way. We just have N, the number of turns in the primary, and the secondary are essentially one and the same. So I wanted to make sure you saw that. There's nothing really special here. I'm not going to put a secondary or primary here for the number of turns. I'm just going to put an N. That is the number of turns. And in fact, while I'm talking, I thought, you know what? I should pass one of these out, or a group of these inductors out. So here is a bunch of old inductors that I've cut out of old electronic devices at different times. This one's out of an old ham radio here. I think actually most of these are out of a radio or some kind of LC filter. I think FM trap is another one that I cut out of. But if you look at these, you will see exactly what I'm saying here is they are a little coil. You can see the wires, you can see it wrapped around, you can see it wrapped around a metal core. So if you want to take a look at them, they're good to see what they actually physically look like, as opposed to these bigger ones that I tend to use here in class for demonstration reasons. But they're, like I said, ones that you're going to see in the lab here real soon. All right, let me keep going here. This then is the derivative of the flux. Okay. Well, let's say this is in the shape of a solenoid. Because at this point, for me to go any further, don't I need to tell you what kind of shape the object has? And so here is a solenoid. And so I'll say, all right, let's look at this solenoid here. What is the flux from a solenoid? Well, the nice thing about the solenoid was that the magnetic field is the same everywhere inside. So when you say integrate it, you really mean just, hey, pull the B out in front. And then the area just becomes the cross-sectional area of this solenoid, right? And so again, notice how we're going to have to take our applications of this chapter and go all the way back a couple of chapters to remember what does a magnetic field look like from a solenoid. And we need to know the direction of the magnetic field. And the direction of the magnetic field is along the axis of symmetry here. So that's where that cosine of 0 comes in. All right, so this becomes an N derivative. Now let me take this one step further. B. B is the magnetic field from the solenoid. Again, going back a couple chapters, what was the equation for the magnetic field from a solenoid? U naught times big N, little n. Okay, I'll put little n for a moment. And then here's the area. But what really was little n? Yeah, little n was the turn density, right? It's the total number of turns divided by its length. So if this is it, I can read right here, it actually says there's 180 of them. Okay, so this would be a capital N divided by L, L being the length of it. So if I were to, maybe I'll put it over here, if I were to say this is L, this is length of my solenoid, and by the way, notice I used a lowercase l. There's a reason for that coming up here, yeah.
So then since the inductor is primary and secondary, the two ends would be the same.
Ah, exactly. So, in this case, since this is the N for the primary, and this is the N for the secondary, as we did last time, and for self-inductance, they're one and the same, there's no point in having a subscript, and I might as well put them together. So I will put minus N squared. These are the same ends. And this is a mu naught, and this is an A, and this is an L, and this is then the important piece of this operation is right there, di dt. In other words, the EMF produced in this case is related to the change in the current. Because the change in the current is what makes the change in the magnetic field, which is the change in the flux, which brings us all the way back to Faraday's law. So because you know Faraday's law from the last chapter, you begin to see that the EMF is produced when you have a change in current. And in fact, you can imagine that for almost any shape. I didn't bring a toroid out here today, but it is one of your homework problems. It says, do the same math that I just did, but use the toroid instead of the solenoid. And you can imagine what's going to happen. You're going to have some numbers out in front, aren't you? They're going to be a little different than this because it's the toroid instead of the solenoid. But you're still going to have a di dt, because the EMF, the back EMF produced, will depend on the change in current and then all the other geometric factors. So here's what we like to do, and some of you have already been working on this. We like to just group these together, put it as one group, call it capital L, and that is what we call the induction of your device. And so this is what the title of this chapter is all about. The induction. This is the inductance. Notice the inductance, as it makes sense, would depend upon, in this case, for a solenoid, it would depend on how many turns you have, squared. It would, of course, depend upon the area of your solenoid and the length of your solenoid. And so those little solenoids going around have a certain amount of inductance. And that inductance is what we label as L. Maybe it'd be better if I'm trying to figure out what part of the board to erase. But here is the simple version then of Faraday's law. If you have Faraday's law in a circuit and it is inducing an EMF on itself, we can always separate it apart to all the geometric factors that affect the flux and then the derivative of the current. And so when you hear that word, the inductance of the inductor, what it means is this number, capital L. That's why I didn't use a capital L here. So the capital L would depend on the geometry. Is this a solenoid? Is this a toroid? Is this a wire? Is this a coaxial cable? Is this a twin lead wire? In fact, I think that's one of your homework, to calculate the inductance of a coaxial cable. You know, what is it? And so we just simply, what I often call the easy way out, bury all this, put it as a constant, and say, there is the L. Oh, a lot of questions. Let's go back here first.
Where did DIDT come from?
DIDT?
Yeah. We lost it.
Oh, my bad. I should have gone right there. Yeah. Thank you. Yeah.
So does that mean that for the solenoid it has units of meters for the inductance?
Of meters?
Well, if you look at the units on each one of those variables, the only thing left is meters, right?
Oh, no. I think you're forgetting the units here.
Yeah.
There's a lot of units here. Yeah, so, okay, so let's talk about the units here in just a second here.
Different for different objects?
No. 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 I mean, the arrangement of this, like if it had a toroid in it, since a toroid has to do with a magnetic field, but it's not a constant, I would have kind of, and the magnetic field in the toroid has a 1 over r shape. When I do this integral, I would expect a natural log. So I bet if I were to work out the inductance of a toroid, I would have the natural log of inner radius and outer radius. I would also expect to have a 2 pi because, again, the magnetic field for a toroid has that 2 pi in it. It has a mu and it has an n squared, so I would expect those two. And like I said, it is a homework problem to work out. And if we have time, I'll even work it out there for you. But simply put, depending on how much detail you want to look on a problem, if you break it down into Faraday's law, you can see what is causing the flux. If you bury all that into a constant, then we can just forget about it. We can even get out a meter and just measure it, and that's what I'm going to show you and we're going to do in lab. We'll just get out our meter and say, what is the inductance of this inductor? Whether it is in the shape of a toroid, whether it is in the shape of a coaxial cable, twin lead, did I say toroid, solenoid? All of the above, right? Whatever its shape is, instead of worrying about all of those, we could just bury it and say that's part of the geometry of it. And we kind of did that with capacitors, didn't we? Didn't we have parallel plate capacitors, right? We also had a spherical one around another spherical one. We had the ones you wrapped up in a coil. We didn't even try to calculate those, but we just said, look, there's going to be some capacitance. Just call it C. And then just bury it inside. So this is probably the easiest one to deal with here, and just call it L. But let's look closely at L, and I think this will help you give a little more understanding of L. There's two ways I like to look at L, two ways I like to look at the inductance. The first one is given right here. If you write this as the magnitude of the EMF divided by the rate at which the current is changing, to me, that actually helps a lot. Because this tells me something about the inductance. This is telling me what? What does inductance say? Well, it really says how much voltage will I get when the current is changing at 1 amp per second. So if I were to tell you the inductance is 7, and I haven't done the units yet, but let's just say 7. What does that mean to you? Well, it means that this little inductor right here would have a back EMF of 7 volts if the current was changing at 1 amp per second, right? That's what it means. And I like that because that gives me a nice way of thinking about what is the reading of the inductor. How much voltage would I get when the current is changing at 1 amp per second? So unit-wise, I guess it comes out to be this. V for voltage, amps per second. Of course, it's a compound fraction, so we'll simplify it a little bit. But that's a good way of indicating what the inductance is. If we simplify it a little bit, we get volts times second over amps. And all of this was put together and named after Henry. So guess what we call these? Henrys. And so we will say our inductor has a certain amount of Henrys. In this case, it would be 7 Henrys, right? Meaning I will get 7 volts if the current is changing at a rate of 1 amp per second. Could be changing at a higher or lower value than that. But like I said, it gives you some physical understanding of it. It's actually why I brought this meter out here. I thought, okay, here is another multimeter one. It's one we haven't used in the lab yet, but it does measure inductance, if I get the settings right. So I have hooked up one of these coils, one of these inductors. I have it set on millihenries. So as I look at this, and for those of you who may be close enough to read, it says 0.13. Okay. So 0.13 millihenries. What does that mean? Well, that means if I were to put current through here and the current was changing at 1 amp a second, it would produce a back EMF of 0.13 millivolts. Not much voltage, not much inductance, but that is this whole idea of the reading of an inductor. Again, nice way of looking at it and saying how much volts will you get when the current is changing at 1 amp per second. If the current is changing at a faster rate than that, well, then you're going to get more volts than that. A lesser rate than that, you're going to get less volts than that. But that's what we mean. And so the unit Henry is probably new to many of you, most of you. Probably all of you who aren't in circuits, since you guys have already done this stuff in circuits here. Well, let's keep going. I said I wanted to solve this thing, and so this was kind of my first step, was to apply Faraday's law to the solenoid and to rewrite it as a minus L di dt. Okay, well, I've kind of erased the circuit, but let me put the equation back up here. The equation I had was the voltage from the external source minus the voltage produced because of Faraday's law minus the voltage because of Ohm's law completes the circuit. And maybe I should have mentioned that. I just wrote down that equation real quick, and I guess I didn't tell you where I got it, but is that okay? And that's Kirchhoff's loop rule, right? That's the sum of the voltage on the three elements, the power supply, the inductor now, and the resistor. And now I want to solve it. So I'm going to take that first step and replace all of that with that. And so that was the first big step, an important step. An important step in terms of the science. Why do we even have an inductance? Why do we even have a voltage? And that's because of Faraday's law. And then once you realize that, now you know the equation for calculating the voltage. It is an L di dt. Put it into the equation. And you'll notice now we have a differential equation, right? We have an I here and an I here. And so as we solved many of our differential equations in the past, let's do the same. Put all your i's together, put all your t's together. If it is separable, fortunately it is, it's the easiest differential equations we can have, because then we can just separate the variables on different sides and then integrate here. And that's what I'm going to do here. So maybe the step to do first is to put the derivative on one side of the equation. And so I get that. Maybe if you look a little closely at this, this will look a lot like the differential equation we had back when we were charging up a capacitor. It's also the same differential equation we had back in our mechanics, where we had air friction or air resistance. And what we did is we tried to get the i's with the i's. And the way we did that is we divided both sides by V minus IR. V minus IR. So that this side of the equation became a 1, and this side of the equation became L V minus IR di dt. And so everything that has an I is grouped together with its derivative, and everything with a t, which is nothing, so it's one of the easier differential equations to have, is on the other side of the equation. And so then when I integrate with respect to time, what will I get? Well, the whole idea of getting all the i's on one side is so that you'll get a change of variables. You'll change it from a dt to a di. This side's kind of boring. That's just a t plus a constant if you like. I'll call it constant number 1. But over here, we've got that natural log again that we saw back when we did the capacitors and back when we did the air resistance. And I think even maybe 1 or 2 other times in this course of this class. But this would be L. I'll just pull the L out in front. And this will be the natural log of V minus IR. And I think it needs to be divided by a negative R if I'm not mistaken. I'll check by taking the derivative. If I take the derivative, that'll be left alone. That will go downstairs. Chain rule will give me a minus R, which cancels that. Perfect, right? And so there's my integral. If I put the minus R over L on the other side of the equation, so there's the minus R, there's the L, I would do a distributive property. I would see it here. But over here, I might as well just call that another constant, because I'm just taking constant of unknown constant and multiplying it by a bunch of other things. And so I still don't know what it is. So I'm just going to call that a constant. I'll find it later. But this would be ln of V minus IR. Now I need to get rid of the ln. You do that by raising it to a power. this would be raising it to a power, which gets rid of the natural log. This e to a constant, well, again, that's just some constant, so I might as well just write it as constant number 3 times e to the minus RLT equals v minus IR. Trying to solve this for I means I can rearrange by putting IR on this side of the equation and e to the minus R over LT to the other side of the equation. Divide everything by R. And finally, I'm getting real close. It's V over R minus C3 over R times e to the minus R over LT. If I think about this at time equals to 0, I want the current to come out to be 0. That's my initial condition, right? So I start here. I guess I've erased my circuit. But if you close the switch and you want the current to be 0 when you get started, then that tells you what the constant C3 has to be. And that actually then says 0 has to equal V over R minus C3 over R, which means then that C3 has to be V, which then turns this equation I into a V over R for both of these terms, which I will factor out and write as e to the minus R over LT. Your author takes one more step. I'm hoping this looks a lot like we did for the capacitor, doesn't it? Physics is a little different because it's a magnetic effect instead of an electrical effect. Okay, but other than that, it's still that same basic equation. What if we called the time constant L over R instead of R times C? But if we call it L over R, then this equation becomes current as a function of time then equals to V over R 1 minus e to the minus t over tau. And so, sure enough, the current looks a lot like the charge. If you remember the charge on the capacitor, trying to debate how best to write it, but when we were charging up our capacitor, we had this, where tau was RC, and that was the building up of the charge on our capacitor. This is that same effect that we have a building up. It's not a building up of charge, it's a building up of current. And so as I close the switch, and I have since erased my graph, but current then as a function of time would be 0, 0, 0 till I close the switch. Then when I close the switch, it's going to have that same shape that we saw for the charging capacitor we have for our charging inductor, if you will. Although I don't really like that word charging. But I'm not sure what else word to use. Because it's not building up charge, it's certainly building up energy. So I guess it's not completely. Energizing is probably a better word there. Yeah. So I'm energizing the inductor here. And so again, just like we did for the capacitors, we're about to do the same thing in this chapter. We learned about, the capacitance. Now we've learned about inductance. We've learned that they build up a charge over time. Here we've learned that they build up a current over time. But this is the equation. And the buildup then depends on the inductance and the resistance of our circuit. Let's see it again. We saw it on Tuesday. It's worth seeing it again. Here it is. I'll hook it up. Here's my power supply, 10 volts. I will hook it to my inductor. Actually, I won't hook anything yet. This will be the switch. Okay, when I touch those together, there's my switch. So I will leave those alone. It goes to my inductor. From my inductor to my resistor. And so here's the decade box that you guys have been using in lab. I will set it at about 750 ohms. I will then go from the resistor back to the power supply. So there is what we are going to call an R RL circuit. And that's what we've just built. A resistor and an inductor with a power supply and a switch. RL circuit. So when I do something like this, what's going to happen is hopefully the inductor is going to energize. It's going to build up that current in that shape. So I can watch it. I will put it on the scope. Oh, and let me get my connections right. There is the ground and there is the voltage on the resistor. And so, if I hook this together, I think my settings are right. I've got 5 volts per division. Each horizontal block is 250 nanoseconds. It's waiting for a voltage. Whoops. It's not quite what I wanted to see. Did I get it? It looks like I got it backwards. That seems right. A volt. Let me try that again. Hang on. Ah. Okay. All right. I guess I should have checked here. DC, power supply. I got something backwards and I don't see it. Ah, looking a little better. I don't like that either. 500 nanoseconds? Ah, there we go. All right, back to 250. I'm pretty sure we had it on 250 last time. There we go. Okay, I think the trigger was just needed some clearing up. All right, well, forgive me for not having it set. But doesn't that look like that equation? Isn't that the rise in it? Let me just make sure it's working again. I'm going to try it one more time. Close the switch. And there is the buildup of the current to 10 amps. If I save that and kind of get ready for another shot, I want to leave that one up there. See how it built up? But what I want to do is change the resistance. What if I lower it? I was at 750. What if I just put it down here to say 350? What do you think is going to happen here? What does that equation say? Okay, so the R gets smaller, so what happens to the tau? It gets bigger, doesn't it? Right? So the decay constant is bigger. It's going to take a longer time to build up here. So ready? 1, 2, 3. And there it is. A little bit longer. In fact, I thought it would show more. I'll go to 250. So here's 250 ohms. And so it's taking a longer time to build up as I lower my R here. And so the physics of it, if you will, is, as a summary here, is I will get a back EMF. That's Faraday's law. And if I put that into my equation, I have not only the resistor and the external power supply, but I have the back EMF. And so that is going to make an interplay. And so what I'm going to get is the current building up, but it takes time to build up based on the time constant. And the time constant depends upon the inductance and the resistance. And that's what I wanted you to see. In fact, let's try the reverse of this. What if the inductor was already energized and I disconnected it? Yeah, and some of you are already guessing it. It would probably be like the capacitor, right? It would probably lose its current like the capacitor lost its charge. Exactly. It will be the same math. The physics will be different because this will be magnetic instead of electric, but it's the same overall answer that you're going to get that decay. So one of the ways to think about our inductors is, of course, to realize that they do have a very similar behavior as the capacitors, except the capacitors involved electric fields and electrical energies and charges. Here we have magnetic fields and magnetic energy and currents to worry about. So what if I had something that looked like this? I had a metal piece that had a small gap in it and a switch. And the switch is just kind of a metal contact that then runs to my inductor and my resistor. Now notice then, here's going to be the new symbol. What's the symbol for the inductor? It kind of looks like a little solenoid, exactly. So that's why we have that symbol. So you've seen the symbols for batteries, right? EMFs. You've seen the symbol for switches. You've seen the switches for resistors. You've seen this symbol for capacitors. And the last one for the semester is inductors. And so inductors use a magnetic effect, which you can see why we had to study all this wonderful stuff about magnetism before we could start applying this wonderful stuff of magnetism. And a good application of it is right here with inductors. All right, and we'll do a few other applications in the next couple of days here, but the truth is, most of our applications will have to wait till your next class in your circuits or your E&M or your antennas or whatever the class takes you in terms of your applications of your magnetic field. But here's what's kind of neat. What if it was left like this for a long period of time? What would happen? Yeah, what would be the current in here after a long period of time? Can you see you've got a V, you've got an inductor, you've got a resistor. According to this equation, or from the physics, however you want to look at it, after a long period of time, what's going to happen? Yeah, that's going to go away. You're just going to get a V over R. It kind of makes sense because when do you get a voltage from your inductor? When there is what? A change in the current. So if you leave this up for a long period of time, as this is trying to show, what's going to happen is it is going to reach a steady current. A steady, constant current. And when it is reaching a steady current, how much voltage do you get from your inductor? Zero, right? We like to say an inductor in that point is like a short circuit. It's like a regular wire. Because you only get a voltage when there is a change in flux. That's Faraday's Law. And so we would not expect any voltage. So the short answer here is, hey, if you're thinking about this and saying, look, it's been hooked for a long period of time, then this would act as just a regular wire. You don't get any voltage because you only get voltage when there's change in current because of the Faraday's Law. So after a long period of time, I would expect the current to simply be V over R. either by taking this equation and saying take the limit as time goes to 0, or by just realizing that an inductor is Faraday's law. Faraday's law is not going to give you any voltage. Without this in the circuit, you just got a V, you just got an R. Okay? Now, here's why I wanted that. So it's been hooked for a long period of time. What would happen then if I moved this metal piece so that it was connected here now? Yeah, see, we're no longer hooked to this battery. Do you see that? But does that mean the current stops? No. Why not? Because as the current tries to change from whatever this value is, V over R, to 0, that is a change in the current. And a change in current in an inductor does what? Creates a voltage. And so this current was already going, say, in this direction. And now you're trying to stop it. Well, let's do Lenz's law. If this was curling around this way, because the current is going around this way, you would have a lot of flux going down. And now all of a sudden you're trying to stop it? Well, that means it would make an EMF. This would be a battery. This would look something like this now. This would be the battery supply from Faraday's law and a resistor hooked back. Would you get any current from that? Oh, absolutely, right? And so what happens here is the inductor becomes the voltage source. It has energy stored in it, as we're going to see. It has a magnetic energy instead of an electrical energy. And when didn't we see the same thing for the capacitor? Where the capacitor had stored energy and it made the current run through the resistor for a while. Same thing here. This will be our discharging or de-energizing the inductor as this goes around. Now maybe I should cross that one out because I don't want you to think like there's some other battery there, but it's the equivalent of that is my point. That as this current is trying to shut down, it is creating a voltage from Faraday's law. And I can't say that enough. Faraday's law, Faraday's law, Faraday's law. This whole inductor is Faraday's law, Faraday's law. If you know Faraday's law, you know all about inductors, right?
So an inductor holds energy by the current increasing? I can't compute how, what do you mean?
Hold off, that's my next step here. Why don't I just, let me just finish solving this and go to the next step, because I want to talk about the energy and then go through the equations in terms of the energy. But the short answer is going to be the energy is stored in the magnetic field that's created from the current. And so as the current is decaying away, we are losing the magnetic field. And it's that energy that was once in the magnetic field is what's producing the current, and which then is making the heat in the resistor as the current is decaying. Yeah. All right, but let's solve this. Fortunately, it's just like this equation, so it won't take us too long to look at what happens to the inductor as it is losing its energy source, or as it is de-energizing. Here. But I will go ahead and write this equation. And as I go around the loop, I would say, well, here's my inductor minus L di dt. Remembering that L is really an n squared, a mu naught, an area, and a length, at least if it's a solenoid. If it was a toroid, it would be some other variables. But that would be the equation for the voltage here. I would get the voltage of minus IR from the resistor, and there's Kirchhoff's loop rule. Just add up the voltage around the loop. Now again, want to emphasize, here's the new piece of the puzzle. You already know about Kirchhoff's rules, and you already know Ohm's law. This is the new one. This is then what and how to calculate the voltage from an inductor. Add it to your equation, solve your equation. If it comes out to be a differential equation, so be it. We're about to see a real hard differential equation before today's over, when we put a resistor, a capacitor, and an inductor all in there together. It is going to be a little bit harder one. Not too hard. Certainly not as hard as any of the things you guys saw in Math 220, but not all of you are in 220, and that's a little above the scope of this book. But as I look at this one, I can rearrange this and solve this for I. So maybe the first thing to do is to leave the minus IR here and to move it to the other side. I do want to be a little careful though with my signs, because if the current is changing, getting smaller, right, then I have a, oh, maybe they, well, never mind, maybe they do match. But I just wanted to make sure that my sign for the current on each of them is the same. And if the current is going this way, then that is also the same direction through the resistor. Okay. If you remember, for the capacitor, we wanted to be real careful with that, and we had to watch our sign. But this one, we still want to watch our sign, but there's nothing real tricky about that one. If I rearrange this, this becomes a minus R over L equals 1 over I di dt. And there's our differential equation. There it is, separable. So again, the easiest differential equation we can have, even though many of you have not been at the differential ones, but you've seen this one. Like I said, this is the one that, even though the author says, hey, these are differential equations, there's stuff that you learned in your 160 class. When they're separable, they're great. You just separate them, you do a single integral, boom, you know, end of story. And so that's what we're going to do here again. We are going to separate everything with an I in it from everything with a T in it, put them on each side, and then do an integral to undo that derivative, which makes that real nice, because this becomes a minus R over LT plus some constant of integration. This just becomes ln of I. Raise it to a power, you have e to the minus R over LT. E to the constant C1 is then equal to I. Again, if we were to call this L over R tau, we would get an e to the minus t over tau. And then if we were to call this some kind of constant C2, there's your current as a function of time. And if we were to look at that current at time equals to 0, we would see that that constant then is the beginning current. And the way I hooked up this circuit was that the beginning current would have been what we got when we were energizing this inductor. And so there's my V over R. And so, well, I'll put a box around it. There's my equation. So this would start here and would decay away if I was plotting current as a function of time. And so there is the first part of this chapter. What is an inductor? Well, it's Faraday's law. What do we measure it in? Henry's. Put it into your circuit. Use Kirchhoff's loop rule here to add up the voltage. Solve the equation, and what we'll see is that the current then is increasing or decreasing depending on whether we are energizing or de-energizing the inductor. Yeah.
So then this would be the function of time current when the inductor is just losing energy, and then the other equation would be when there's a power with a voltage source included with it.
Right, right. So his question, for those of you who didn't hear, is this is the equation for when the inductor is not hooked to a power supply, when the energy in the circuit is coming from the inductor itself. And so this is what would be happening here, because you would have something that looks the equivalent of this one I just crossed out. You have a power supply with a resistor. That's a terrible resistor, and you're doing that. But your power supply, its voltage keeps changing with time, because the voltage is based upon how the current is changing with time. And so you can imagine the current would change based on the voltage of the power supply, and it's an exponential decay. Oh, fair enough. Yes, yes. Maybe it might have looked better if I said it was the original current times e to the minus t over tau. And that's the original current. And then I have to go back and say, well, how did I get that original current? And in this case, the original current came from hooking it up to this power supply. Yeah. Because it could have been hooked up to some other complicated circuit to get its original current. Yeah.
And this one has no back EMF, and the other one, that's what you have that minus sign, because that back EMF on the voltage state.
Right. And you might not call this, I don't know if you want to call this a back EMF. When it was building up energy, it was opposing the current from going in. In this case, it's opposing the current from stopping, right? And in fact, it might be even worth asking here, this is always an interesting one, what happens to an inductor if you try to disconnect it quickly? I mean, I had it switch over so I could watch the current decay, but what if this was just a plug? I mean, you remember some of the other problems we did where we had, say, an electric motor. I mean, let's just say this is a vacuum cleaner. And what I do is I have my vacuum cleaner plugged into the power supply. So maybe here's the wall. I plug it in. The current goes through all these coils. Isn't that how we made an electric motor? And so that electric motor has a lot of induction with it. Now, the point of that electric motor is to make parts move, so it has nothing to do with the induction in terms of delaying the current from building up or keeping the current after. But the consequence of how you build a motor is the fact that it has a lot of inductance. So what happens if I walk over to my vacuum cleaner and I try to pull it out real quick? Exactly. You can't stop the current right away because the voltage produced by that inductor is proportional to the rate at which you're changing the current. So if you try to unplug it really quickly, you're trying to shut off the current real quickly. As you try to shut off the current real quickly, you make a large voltage. Maybe 1,000, maybe 10,000, maybe 100,000 volts. But it'll be a lot of voltage that the current will continue. It will jump through the air and you will see a spark there. The biggest problem could be is if it was so much voltage, the spark was not there at the plug, but the spark was between two sets of wires that are in the motor. And now you've burned through the insulation in plastic and just fused those two wires together, and now your motor's been damaged. So that's the big problem of the quick shut off. And so most of them are designed with extra circuitry, so when you hit the switch, the current doesn't shut off automatically, but goes something through this, and the current decays through a resistor at a slow rate so that the voltage doesn't get real high, so you don't short circuit out your wires.
Is this how energy recapture systems work on electric motors?
No, that's something a little different. And the short end of it is, as the motor is spinning, you now make the motor a generator. And if you remember from some of the last chapters, a generator and motor are essentially the same thing. And so you take the motion of that motor and now make it a generator, and you leave it charged to the battery, and you send the voltage back into and recharge the battery. And so they're not just trying to decay it away and get rid of it. Yeah.
So those wires would have their own inductance.
Oh, the great question by itself. What if you had just that? Do you have any inductance?
It's a wire, right?
Yeah. You have some inductance. Because there is going to be flux. As the current flows this way, there's going to be flux. And you got a single loop. Now, you don't have much inductance. And so this small little circuit has some inductance, and it may be important, and we may have to consider it. Just like those small little wires have capacitance too. And so I cannot fully understand a circuit unless I understand inductance and capacitance, even if all I hook up is a resistor and a battery, because I have wires which make inductance. And then those wires have size to them. They make capacitance. Granted, those are small. And up to this point, we've ignored them. But you will soon see them, and you already do see them. Do you see these little oscillations? That's caused from the capacitance of those wires. And so we'll see what happens when we have an inductor and a capacitor. And we'll see we get oscillating voltages. And you're seeing it here. I don't have a capacitor hooked up to that. Or do I? I do. And so I've got to, add to any circuit. Even the very simple ones that we got started with back in day one of this class, where we just had a battery and a resistor. The truth is we had a battery, resistor, capacitors, and inductors in there. We just hoped that the capacitors and inductors were small enough that nobody asked me about those little oscillations. Because you weren't ready to hear it yet. And now you are ready to hear that. And that's what we'll do next. But as promised, we got to talk about the energy. And so let's look at this circuit again. Let's write out this equation. Let me come back now that we've solved the equation for building up the current in the inductor. That is what you might call energizing it, and the current as it is de-energized. Let's look at this equation a little closer. We had a V minus an L di dt minus an IR equals 0. Fair enough? Let me move the negatives to the other side of the equation. And let me multiply both sides by I. And let's study this for a second. I'll start with this. What would you call this? Power where? Yeah, this is the power being delivered by my voltage source. So if the switch is in this location and it's building up, and I'll put my inductor back here, okay? Then this would be the power that is being delivered by my external power supply. Fair enough? Where does that energy go? Well, that's what this is saying. Let's look at this one. What's this? That is the energy, or the flow of energy, rate of time, power, where? In the resistor. That's the I squared R that we saw a few chapters ago. So obviously some of the energy that is coming from here is being consumed here. And this is why that resistor is going to get warm. Okay. And what else do you see? Yeah, so what's this? And that's our main focus. What's that? Yeah, that's the power going into the inductor. This is the part of the energy that you had asked the question earlier. This is saying the rate at which energy, and I'll put U for stored energy. I'll put an M for magnetic, although now that I think about it, I think your author puts a B for magnetic, so maybe I'll do that. Try to be consistent with your author there. So, okay. He's saying the rate at which energy is going into that inductor, and it's being stored in a magnetic field, because we know that the current's getting bigger and bigger and bigger. And what do we know about a magnetic field? It's related to the current. And so the rate at which energy is going into my inductor is equal to that. It's the rate at which the current changes. And this will set up a perfect equation for, let's solve the equation for the energy in an inductor. If you integrate both sides with respect to time, what do you get? Well, DTs cancel off and you get the equation I'm looking for right there. What is the energy stored in the inductor, which is in the form of a magnetic field? And when you do this, you get L I squared over 2, which we usually write as 1/2 L I squared. And so this inductor is storing an energy Its energy is based upon how much current it has. Which hopefully isn't a surprise, because isn't the current telling you how much of a magnetic field it has? And in fact, if we go back a few chapters, didn't we have the same equation for a capacitor? Didn't we say the energy for a capacitor is stored in its electric field? What was the equation for that one? 1/2 C V squared, right. And so you can see the connection or the analogy between the inductor and the capacitor. Both of them are being energized. The capacitor is getting its energy based upon the charge you put on it, which is why it got a voltage. The energy is stored in its electric field. The inductor, on the other hand, has energy. It is being stored in the magnetic field, which is based on how much current it has. That's why when we had closed the switch, that's where the energy came from. The energy that allowed the current to run for a little bit. Or put another way, here's what you did. While you had the switch in this position, you put some of this chemical energy into a magnetic energy. And then when you moved the switch the other direction, you took that magnetic energy and turned it back into electrical energy, which showed up as heat a little bit later as our resistor warmed up, as we were discharging or de-energizing the inductor. And again, hopefully you see that, hey, we did that for the capacitors. We're going to do it for the inductor. Just remember, the inductor is magnetic, and the inductor has to do with current. So obviously there are some differences between them. But the analogies are there. Yeah.
So if you divide both sides of that equation by current, you get voltage on the left and then equal to 1/2 Li
If I divide both sides by what?
by the current I.
By current I? So I get magnetic.
I'm sorry. You have to, never mind.
Okay.
I was thinking of power.
So let's say your inductor energizes, and then you come along and disconnect it from the wire. Disconnect those wires. Like, what happens to the magnetic potential?
Well, that magnetic energy is going to show up somewhere. Okay? Most likely it's going to show up in a current. If you tried to disconnect it quickly by just cutting it, the disconnect that you're trying to do so quickly creates so much voltage that I don't care how quickly you try to pull it apart, it's going to do that. And you're going to get a spark. And your parts could very well get damaged, which again is while a real system is built with some kind of other internal circuitry, so that as somebody goes to unplug it, either accidentally or on purpose, it really doesn't make a big enough spark to damage it. It does, and sends that energy and that current elsewhere in a bypass resistor. So all that happens is that bypass resistor gets hot.
Okay, so I guess my question essentially was, so magnetic fields don't, I don't know, maybe lack of better word, they don't dissipate. They discharge their energy.
Right, or put another way, I think is what you're getting at. This is conservation of energy. If we've got energy stored in a magnetic field, it's going to go somewhere. You lose that magnetic field, it goes somewhere. To get the magnetic field, you have to have put in energy from something. So in this case, we've got to lose chemical energy from our battery in order to build up the energy in the inductor. Then when we throw the switch, that magnetic field's got to go energy. Probably the classic case of magnetic fields disappearing and going somewhere is what we call solar flares. The magnetic field that builds up on the surface of the sun can be enormous. And it's all these moving charges, these plasmas on the surface of the sun. And then that field will dissipate as all the charges run into each other. But where does all that energy go? Kinetic energy. And all these particles come exploding off the surface of the sun. And that's our solar flare, as billions of particles are traveling billions of miles an hour and racing through space. And so magnetic energy converted into, in this case, kinetic energy. Right? And so there is your energy. Now, we didn't take too much time, but it's probably worth doing it now for this capacitor as well as the inductor. Let's take a closer look at this inductor here, particularly this energy. This will help, I think, give you a better and deeper understanding that the energy really is magnetic. It's not energy in the current. It's the current makes the magnetic field. That's where the energy is. Let's look a little closer at L. If I write this as magnetic energy is equal to 1/2, we solved for L, at least for the solenoid. So let's go back to our basic physics. Let's put L for what it really was. Do you remember what L was? It's been a while, 40 minutes or so. Wasn't it an N squared, a mu naught, an A, and an L? Wasn't that the inductance we did? In fact, I got to check myself. I'm pretty sure that's what we derived. Yeah? Okay. For that inductance. And then if I multiply it by current squared, let's take a close look at a couple of symbols here. To make things work out, I'm going to multiply the bottom by L, and of course, to balance it, I got to multiply the top by L. Fair enough? Okay. If I multiply the top by mu, I have to multiply the bottom by mu, right? Now, in case you're wondering why I'm doing that, here's what I want you to see. For a solenoid, what is that? What is N over L times mu times I? Isn't that the magnetic field? All right, so what this comes out to be is magnetic field divided by mu naught equals, and look what I'm left over with. Change colors. What's this? Isn't that volume of my solenoid? I'll hold it up here again. Didn't we say the area was the area of where the flux was, and L was, the little l, was the length of the solenoid. So this is the volume of that solenoid. And so let me just spell out, well, VOL, so I don't put a V. I don't want you to think it's voltage or velocity, right? But I think when you write it in this form, it looks a little nicer. This is saying the energy per volume, what we would call the energy, well, energy per volume, an energy density is equal to what? Well, the strength of the magnetic field. Now, it's the magnetic field squared, so if you doubled the strength of the field, you would quadruple the amount of energy that's stored there. But I think it gives us some insight to saying, where is the energy in this inductor? It's stored in the magnetic field. Now, the magnetic field comes from the current, so you can't have the energy without the current. But I want to emphasize, the energy is not the current. The energy is the field. The energy is inside here. There's an energy concentration, an energy density where there is a field. And we really could have done the same thing with the capacitor. I know it's been a few chapters ago, but let's take a closer look at the capacitor too. What did we say the capacitance was for a parallel plate capacitor? I know it's been a while. But I'm sure you're reviewing knowing the final. 2 weeks away? That's a scary thought, huh? 2 weeks away. 2 weeks from today. By the way, what classroom is it in?
Here.
Oh, here? Oh, that's obvious. What time is it? 8 o'clock. That's not so obvious. Okay? 8 o'clock.
So
Okay.
the final is not in 2 Tuesdays?
On 2 Tuesdays?
It's not next Tuesday, but the Tuesday after?
Yeah. Did you think it was next Tuesday?
No, I'm asking you. I thought it was later. That's really soon.
Yeah, no, it's really soon. We only have this week and next week of the regular semester and then finals week. And you guys are on Tuesday of finals week. So, all right, well, good. I'm glad I brought that up. So, Tuesday, and again, remember, it's 8 a.m. That's always a scary thing there. Okay, so it's an hour earlier. All right. But no doubt you will have reviewed, hopefully, in the next 2 weeks for the parallel plate capacitor. It was epsilon naught A over D. So that's the capacitance of a parallel plate capacitor. Voltage is the electric field divided by D. If we square that, look what happens here. If we group the 1/2 epsilon naught E squared together, I'm sorry, I wrote that wrong. It's electric field times D, not divided by D. Electric field times D squared. And if I get the E squared together with the epsilon naught together with the 1/2, then I got area times D. What's this? Volume again, right? And so we didn't spend too much time on it because we really didn't need it till we start to get into chapter 34 here, which I'm not sure how much time we'll have for chapter 34, but we need to say the basic physics here is there is energy stored in the capacitor. Where is that energy? It's stored in the electric field. And so this is energy density 2. And so in our capacitor, we had stored energy. We called it an electrical energy. The energy was actually stored in the electric field. Likewise here. For the inductor, we have energy stored in our inductor. That energy is in the form of a magnetic field. They're both proportional to the square of their fields. All right. Okay. Now that we've got a good first step where we put a inductor together with a resistor, what do you think might happen if I put 2 inductors? What if my circuit looked like this? Here's that power supply again. There's V. Here's my switch, S. Here is my inductor, which I will call L1. Here is my next inductor, which I will call L2. Here then is my resistor. Now what am I going to do? And so hopefully you see, okay, we've done the fundamentals, right? 1 inductor, 1 resistor. What happens now if I have 2 inductors, 3 inductors, 2 resistors, 3 resistors? What are you going to do? Yeah, it's probably worth asking, is this equivalent to anything? I mean, we had resistors that we could put in series and parallel and find their equivalent. We had capacitors, series and parallel, that we can find their equivalent. Can you do the same thing with inductors? And sure, you can. I claim that there is an equivalent to this. And if you look at the equation, you'll begin to see it. Let's do Kirchhoff's rule again. This would be a minus L1 di dt. But because these 2 inductors are in series, doesn't it mean, when anything is in series, that they all have the same current through them? So I'm not going to write current 1, current 2. It's not needed. But if you look closely at this equation, this would be V minus L1 plus L2 di dt. And I'm hoping you can see that that's really the same equation we solved, what, half hour ago, 45 minutes ago? Except what? This then is the equivalent inductance. So the equivalent inductance is L1 plus L2 when you hook them in series. And that's the same type of formula we had when we hooked resistors in series, right? But not capacitors. So we got to keep it straight. How do we combine them together is important. You first have to recognize, are they in series or are they in parallel? Then when you know if they're in series or parallel, you have to know how do you combine them. And we noticed that the resistors we combined one way and the capacitors another way. Fortunately, the inductors are like the resistors, if you can remember that the equivalent inductance is just the sum of the two. So if I were to close this switch and ask you this question, what is the current as a function of time? You would say? V over R. Right, minus T, okay, over tau. But what's tau? Right, and so tau would be an L1 plus an L2 over an R, right? Shall we make it harder? What if I had inductor 1, inductor 2, resistor 1, resistor 2? Could you do that one? Oh, good. It wasn't that hard? All right. So hopefully you're seeing that here I've got two resistors in parallel. Couldn't I get its equivalent? Here I have two inductors in parallel series. Did I say parallel? Parallel series. I can get their equivalents. Once I got their equivalent, it's really the same equation, but I can write it out this way. Right? Now, maybe I should try this one. I'm hoping by extension you can see this one because I want to move on with time and not actually prove it to you. But what would you think would happen if I had inductor 1 and inductor 2, resistor 1, resistor 2? How about that circuit? All right, so without proof, I'm going to say that the equivalent inductance is 1 over L1 plus 1 over L2. This is what you get in a parallel circuit. And yeah, so 1 over L equals, you know. So my equivalent inductance then is an L1 times an L2 over L1 plus an L2 when I get a common denominator and then flip it. And so when I go to find out the current is, again, a V over R1 plus R2, right? The equivalent resistance. 1 minus E to the minus T tau, where tau is, okay, L1, L2 over L1 plus L2. So there's the equivalent L divided by the equivalent R, R1 plus R2. So again, by extension now, we can really do some pretty complicated problems with the equivalent circuitry. We only needed to solve for one inductor and one resistor, and then realize that if we had a bunch of resistors or we had a bunch of inductors, we can put them together, as long as they are either series or in parallel. Is it possible that you could have neither series or parallel? Yeah, it is, and we did that with resistors. We won't do that for inductors into the semester. So all of our inductors will either be series or parallel. We'll wait till next semester before we, or your next electronics class, before we do maybe some other little mixing up here. But I think you know the answer. Couldn't you just write out the loop of your equations and have a system of differential equations and then just solve the system of differential equations? Now, granted, the math's not so easy when you go to solve a system of differential equations, but certainly the idea hopefully seems pretty straightforward, that, hey, write out the basic laws of physics, and physics about knowing how to apply a few powerful fundamental concepts to explain a universal phenomenon. So you just, hey, write out a couple of equations. And if they're hard equations, then you're just going to spend a couple hours or pass it off to your math buddy and say, can you solve this, please? I got a system of equations, and they're really hard. Or punch them into a computer, or simplify them, or all these other little tricks we like to do in science and engineering when physics is straightforward, but then the actual answer to the equation is pretty intense. Well, it's why I brought this out here again, is I thought, oh, let's give it a try here. You guys saw me hook up this inductor. It's still hooked up. It's reading on the millihenries, so it is 0.13 millihenries. What if I took a second inductor? I wonder if you guys can, it won't stay. Right. Prop it up there so you can see it. At least some of you can see it here. What if I were to take a wire so that it would feed into this second one, which I'm going to assume is nearly identical. So if that one was 0.13 and this is 0.13, I put them in series, I get 0.26. Okay, it rounds up to 0.27. Right? On the other hand, if I were to put them in parallel, I guess it would look like this. There's the first one. And if I put them in parallel, what should I get? .13, about half of 0.13, right? 0.065. 0.065. So sure enough, it does work. Let me go back to series, because there is one other thing that nobody asked, and I'm glad you didn't ask. I was hoping nobody would ask it, but I'm hoping it's obvious too. If I hook these in series, and I'll leave them for a moment and come back to this equation, I'm thinking I left something off here. Let me kind of clear this part of the board here. Let's see. I go around the loop, and I'll put it in a different color. There's V. There's minus the voltage produced from the first inductor, right? And then over here, here's minus the voltage produced from the second inductor. And then this is minus the voltage from the resistor. Okay. Well, maybe I should have gave myself just a little more room here. Minus IR equals 0. But if I look carefully at this, what is this term saying? Isn't this the voltage produced because of Faraday's law? I mean, isn't this the voltage produced because there is a change in current inside of itself? But now wait a minute. Isn't this guy near that guy? Shouldn't this guy have a voltage produced because of the change in flux created by this one that's in that one? So I would think there should be what we'll call a mutual inductance. The overall inductance is not just the flux created from yourself in yourself, and the other one from yourself in yourself, but it's how does this one affect that one, and how does this one affect that one. And so we like to use the word mutual inductance for how is one affected by number two based on the current that is in number two. Although in this case they're in series, so there's no point in calling it current number one and current number two. And then likewise, doesn't the same apply to the other inductor? Doesn't the other inductor have a EMF produced because of the flux in itself, but also an EMF that is affected on number two because of the change in number one? Wow. That's a more complete equation. That is what we call a mutual inductance. And so if you remember an hour ago when we started, or an hour and a half ago, I said, what's this chapter about? Well, it's about inductance. Mostly self-inductance. But also, there's mutual inductance. And to be quite honest, we kind of leave it at that. We just kind of throw out the concept. Don't forget that these inductors can crosstalk to each other. And the effect on one inductor, and how does it affect the other one? And that's what we mean by a mutual inductance. You can see it here. That's why I wanted to hook this up here. Let's see if I can get this maybe a little better prop up here. I don't know if that's better. But when I put these two in series, I got a 0.27, right? But really what we did is calculated it when they were far apart. Because we are really saying the flux from this one does not affect this one. We did not consider the mutual inductance. Now fortunately, as you can see, if I bring them close together, it barely changes. And so we'll just say, okay, let's throw you the concept of mutual inductance. Let's worry about it next semester when you get into your more advanced circuitry. But can you, for those of you who are close, can you see it change by just a little bit? In fact, you can probably really see it change if I actually feed one into the other. And so it went from 0.270, for those of you who can't see the numbers, down to 265. And if I flip it around, then the flux in one help and complements each other. So it goes up to 2.75. So I get a change of 10 parts in roughly 300. So not that much of a change, depending if the inductors are lined like this, or if they're like this, compared to far apart. And so I may or may not want that. It's why I brought this old circuitry. This is an old FM trap off an old antenna, and you guys are way too young to remember, but you used to get your TV channels through the airwaves, and you put up an antenna on your roof, and you didn't have this cable and internet thing here anyways, but the airwaves, and you put up this antenna. And the antenna was great because it picked up TV signals. It was a pain because it also picked up FM radio stations. And the FM radio stations would leave ghost marks on your channel. So if you're watching particularly channel 4, you would have all these streak lines in them because of the local FM channels. So you wanted to, what we call, trap those signals before they went all the way down your antenna post and into your television set. And so this would be midway. So you would have your antenna, you would have your FM trap, and then your TV signal would continue on out. But look at the design. The electrical engineers who designed this took clever. They've got 1, 2, 3, 4, 5, 6, 7 inductors here. And they've aligned them to crosstalk. You can see that these two are close to each other and parallel to each other. So they want the flux from this one to influence the flux of that one. But this bottom one is rotated at 90 degrees with the idea that the flux created by these upper ones do not really go through in a normal position. They go, the dot product would be 0 when they go through here. So these 3 down here are deliberately put perpendicular to these so that there is no crosstalk. And then these are aligned close to each other, next to each other, so these crosstalk. And I would assume that these are far apart, so they don't crosstalk. And so take advantage of the mutual inductance or not take advantage of the mutual inductance. So I don't know if you want to look at it and pass it. But the design, the actual physical design on the circuit board now can begin to take shape. And for those of you who go into the microcircuitry and start building microprocessors, this is the challenge. How do you build a piece of electronics that is faster and faster and faster? How do we build transistors that are faster and faster and faster? As they switch faster, you get more induction. As you get more induction, the changing of one affects the change of the other. They're close together, they're changing quickly. And so you want to be able to design it so that they don't affect each other. Or they do affect each other, depending on what you're trying to get here. But the actual placement on the circuit board would matter. These two in the same direction close together means these become more important than they would have otherwise. And that's your mutual inductance. Yeah?
So we're not going to go over how to calculate that?
So no, we're not going to bother to give you any equations or any calculations. You kind of know it. you would have to calculate, well, maybe you don't know it, you would have to calculate how strong is the magnetic field from this one when you are a certain distance away. And I guess we've only calculated magnetic flux from a solenoid as if it is infinitely long. So I guess we really don't know how to calculate it. But, and so we couldn't calculate it. But we could at least set you up for your junior year where you will calculate the magnetic flux in a solenoid that is not perfectly infinite long. In fact, I could give you a rough estimate, is we didn't have it in our book. The author took it out a couple of editions ago. He used to have a finite size inductor. It's pretty easy. You know the flux from a ring, right? So can't you just add up a number of rings? And so you can cut the ring infinitely thin and add up the flux there. And don't make it infinitely long, make it finite in size. And you can get the flux. So you start with a ring, add it up, now you get the flux outside. Once you get the flux outside, you can know how far you are, and then you know how much flux goes from one to another. But again, really beyond the scope of this class. Well, one last thing then. What if we did this? The last part of this chapter is to say, let's throw a capacitor into this mix. Okay? We've already done capacitors. And so I'll say it again. You'll notice this chapter, we haven't done anything new in terms of physics. But we have taken Faraday's law and applied it to a solenoid and said that's an inductor. And then we put the inductor into the circuit with a battery and a resistor. Then we did a bunch of inductors, right? And a bunch of resistors. Now let's do a capacitor. Or maybe even a bunch of capacitors with a bunch of inductors. But let's start simple. Let's start with one capacitor, one inductor. Maybe I'll put a switch here to start the whole thing off. So maybe step one is to come over here and give the circuit some energy. Now I could do that by either putting current through the inductor, but it's a lot easier just to put charge on the capacitor. So I will. Let's come back over to here. I can disassemble this contraption. I'll put my measuring device of my scope over here. I will have my power supply, and you might remember our circuit board from lab with our capacitors. So I will put that 10 volts right onto that capacitor. So simply put, I guess I have externally added a voltage supply. And at this point, I have not hooked up the inductor, but I have closed this switch and have now, sorry about that. That looks funny. Okay, try that again. All right, so I now have hooked up my capacitor to my power supply, and in this case I've got a bunch of positives and a bunch of negatives over there, right? And what I want to do next is ask this question. What would happen if I then open this switch, so I disconnect my power supply, and then close this switch? Well, anything will happen. Yeah, this capacitor is now charged, right? It's like a battery. It's got energy stored because of its electric field, right? It's got a voltage because of its an electric field. And so what will happen is it will start sending current through the circuit, right? It'll go through the inductor. And as current goes through the inductor, what begins to happen in the inductor? It builds up a magnetic field. We're beginning to energize the inductor. And so it may take a little while. How long? I'm not sure. But what will happen at some point is all the charge will have gone off of this capacitor as the current is building up and building up and building up and building up. If I was making a plot of the current as a function of time, or for that matter, the charge on the capacitor as a function of time, I guess the first thing I would see is the charge would go down, down, down. I would start with some initial charge. And I have yet to prove it to you, but it will arc in this shape. But we will lose charge. And in the process, we will gain current. But eventually, all the charge will come off the capacitor. Is that the end of the story? Yeah. Here's where the fun begins here. Is now we have an energized inductor. And what will it do? It does not want to change its current. It will become the EMF. It will make this side positive and this side negative. It doesn't want to stop this current it just acquired. It will keep pushing it through, and so what begins to happen is the charge begins to build up in the opposite direction. And it begins to push it this way. But of course, as this builds up charge, it is opposing that, and eventually it's going to reach what I would call a maximum negative charge. And so the current now decreases and comes to a stop. Question?
I was going to ask, don't you have to have a resistor for that circuit?
Well, how about the wires?
Because it wouldn't just go back and forth forever. You'd have some resistance.
Okay, but let's talk about it with no resistance first, and then the reality is you're always going to have some resistance. But I'm going to hook it up in a second with no resistors, but of course my wires have some resistance, so we need to talk about what happens if it has some resistance. But with no resistance, this is a much like what you saw in your mechanics. What if I took a mass on the end of a spring and I were to pull it down to get it started? That's here. Energy stored in the capacitor. If I let it go, what happens to that energy? Yeah, it goes from the spring into kinetic energy. And it gets back to equilibrium. And in equilibrium, we have no charge on the capacitor, but we've got a lot of current in our inductor. And it doesn't stop there. Because of the momentum, it keeps going up the other side. Because of Faraday's law, it keeps generating a current the other direction. And this spring would go all the way up, and just like the charge would go all the way the other direction. And in fact, once it got fully charged in the opposite direction, guess what's going to happen now? Just like the spring, it's going to come back the other way. You're going to push current in that other direction. And so the charge is going to get lower. The current is going to increase in a negative fashion compared to the first time, which would be the positive direction. And so I would get some kind of oscillations like, well, maybe I'll just do one cycle. And I guess I should keep them together in terms of time. And so there would be one cycle. And this would be just repeating and repeating and repeating and repeating. And if there was no friction and no air resistance for a mass on the spring, it would keep doing it forever and ever, right? Same thing here. If there was no resistance in this circuit, it would keep doing it forever and ever and ever and ever. Let's give it a try over here. All right, so let's see. I'll clear this. Turn off that waveform, get it all ready. Okay, and say, all right, here is my capacitor. It is fully charged, if you will. Let me hook up, trying to think of the best way to do this. Why don't I get it sort of ready by hooking up my inductor here. I will disconnect my capacitor. I just don't want to do it too early because capacitors don't really keep their charges forever and ever and ever here. So I'm going to disconnect this one in just a second. And when I do that, I am then going to hook this one up. But I would like to watch it. So I will hook the scope up also at the same time and take a look at what I might get. So I will disconnect the capacitor and connect the inductor. Let me hook it again and change our setting again. Vertical. Oh, we're on DC. That's good. This happens, looks like a little faster. So let's try it again. And hook it up. Oops, that's too fast now. Okay. And let me go back to that. But if I hook this up, oh, got to clear it. Okay. There we go. That's what I wanted you to see. See the oscillations? See this little part here where, of course, I hooked it up, so it's going to go to 10 volts, but it's going to then oscillate back and forth, back and forth, back and forth. Let's solve the math. Shall we write out the equation? Shall we do the loop? Let's see. As I look at the math here, I would say, all right, the voltage on the capacitor plus the voltage on the inductor makes the full loop, right? All right, so how do I calculate the voltage on the capacitor? Well, isn't that charge on the capacitor over the capacitance? All right, and of course it's going to change as a function of time. How do I get the voltage on the inductor? Well, and that minus L di dt equals 0. So there's my equation. And again, like I joked a little moment ago here, is we already know these rules, right? Write out Faraday's law together with Kirchhoff's rules, get an equation. If it's a differential equation, so be it, solve it. Now this is going to be a second order differential equation, so this is going to take a little more thought in solving it than what we've seen so far. But fortunately, it's the easiest second order differential equation. So it's a little harder than our separation of variables, but not a real hard one here. So let's see what it comes out to be. I'm working in green here. And so let me put Q as a function of time divided by C equals L times di dt. Isn't this I related to that Q? How is I and Q related? Okay, so I is the derivative of Q, right? Almost. Isn't it negative in this case? Why negative? Well, what does Q represent? The charge on the capacitor. So dq would be a negative when it was coming off, but I labeled that as a positive in my inductor. So I got to be a little careful here with my signs. But once I see that in my signs, I've got Q over C equals a minus L times the second derivative of Q. And I'll put the minus on this side of the equation. I'll put the L and the C together with the Q, and then I'll put it as a second derivative of Q with respect to T. So that's what I meant by, are we going to get a differential equation? Oh, absolutely. But it's a second order differential equation. And unfortunately, those you can't just separate the variables and integrate once. But this is a simple second order one. In fact, you can almost get this by inspection, I hope, yeah.
If the sum of both of those add up to the voltage of your source, how does it oscillate above 10?
Let's see if I'm saying this right. What I have here, and you can't see it in the short time frame I have, is I have both oscillations and a decaying circuit. In other words, what I actually hooked up here and what I have here is a little misleading because I did not put a resistor in here. Fair enough? So what I should have is a combination of the decaying of the circuitry. And you are only seeing this part right here up at 10, and you're seeing the oscillations around 10. And so we're focused on just that part of the graph. And so it's going plus and minus as it decays away. Yeah. And so we're hopefully we'll have enough time to just throw in a resistor at the end here. But the simple case is with no resistance, and what I have does have some resistance. Can you solve this one then for Q? And since we're low on time, I'm not going to go through any fancy math techniques. Some of you have already been doing it in 250. But at this one, I don't think you need it. I mean, look at this. Ask yourself, what could you take the derivative twice of and end up with negative of the same thing you just took the derivative of? Sines and cosines, right? Take derivative of sine, what do you get? Cosine, take derivative of cosine, what do you get? Negative sine, that's how you get negative. I heard somebody say exponential. No, exponential wouldn't give you the negative. You take the second derivative of exponential, yes, you get back to an exponential, but you don't get the negative out in front. And no, it doesn't work with e to the negative exponential either, because you get a negative twice, which just gives you a positive. So no, it doesn't work for exponential, but it does work for sines and cosines. So what we should have then is, and I'll just label it as a cosine function. What? Where does this come from? You know, what if I had sine of a times t? Take the derivative of that. What do you get? Isn't that how the a gets out in front? Isn't that how you get numbers out in front after taking derivatives? The chain rule? Exactly. And then if I did the derivative again, I'd get that, right? And so there's the negative, there's the constant out in front, and there's the sine function. And why'd I do sine here and cosine there? That's probably not good teaching. But you see the same thing there, that whether it's a sine or a cosine, you take its derivative. This then inside must be 1 over the square root of LC times t. And so this must be the initial charge. Yeah, and since we're low on time, I won't actually take the derivative, but I wanted to take the derivative to show you it will work. When you take the derivative of this twice, you will get back to a cosine function. And in the process, you will get a negative. And in the process, the chain rule will bring this out twice. And so this then is the frequency. This is the rate at which it goes back and forth. That is, these little oscillations go back and forth, back and forth, back and forth, back and forth. And so that's why if I made a plot of this, I would get something that looks like this. And probably doesn't surprise you that A, it oscillates, because that's what we said would happen here. And then B, the rate of oscillations would depend on both the inductor and the capacitor. And so this LC plays a good role. This is why we call these LC oscillations, because you get these LC oscillations even if you think you don't have. And you saw it earlier on. You didn't think I had an inductor when I just hooked that up. And did you not see those oscillations? Because I really do have an induction. All those wires have some induction parts to it. Many of you who work in the electronics will probably come across a lot of your cabling. And when you send data down a cable line, they will take the data line and they will twist them. Why? Twisted pairs. What are they trying to do? Reduce the magnetic field, right? If you just had a wire here and a wire here and the current went down one side and back the other, you'd get a log magnetic field inside there. But by taking the wire and twisting it, this part has the field going up, this part has the field going down, this part has the field going up, this part has the field going down. So your twisted pairs have a much lower induction. And the much lower induction means you can send your data down at a faster rate and you don't have to worry about the oscillations. So your twisted pairs would be much faster than your non-twisted pairs, although they're still not as fast as your coaxial cable, not even close to your fiber optics. So, it depends what kind of cable you want and what you're trying to get. Well, one more step here, and we'll call it the end of the chapter, and that way when we come back on Thursday, we can start the next chapter. But what do you think would happen if I threw a resistor in here? And you probably can guess it just by looking at my real experiment compared to this make-believe experiment. It's a terrible drawing, but they're supposed to be the same height, right? Up and down, same height forever and ever and ever and ever and ever. Is that what happened in this real one? No, why not? Yeah, because really, in addition to a capacitor and an inductor, there would be a resistor. So to make this complete, we really needed another minus IR in the equation. And so that was really a dq dt times R. And so that means over here, we should have had a first order derivative with the R, I guess divided by the L. Now that one's not so easy to see. What function can you take its derivative twice? You end up with negative of the function, but you also end up with the first derivative. Well, you might guess that it's probably a product of two functions, because isn't the product rule say when you take the derivative they become two pieces? And so this being really the first derivative of that, so this tells me it's exponential. This tells me it's sinusoidal. So the final answer is really, as you might expect, a bit more complicated. It's exponential and cosinusoidal. And this, oops, I'm sorry. It's not quite that simple either. I'm going to have to look it up. So without solving, and nor does your author solve it. He says, look, this is a second order differential equation, fortunately with constants out in front. So it's one of the simpler second order differential equations. And those of you who've had differential equations probably won't have any troubles solving it. But your author does not try to solve it. He just says, check this for the answer. It will work. And so as your education continues, you will do this. In fact, I'm pretty sure students have talked to me in the past that they do a lot of this in the Math 220 class. To try to make it practical, they say, hey, a good example of a second order differential equation is an electronic circuit that has inductance, capacitance, and resistance. And so they go, and obviously the point is to teach you how to solve the differential equations, not to teach you about the electronics. But that would be the solution. Oh, and I guess I better put a initial charge out in front. So that's the exponential decay. And isn't that what you see? Don't you see both the exponential decay and the oscillations? And so that's what a real one would look like. Yeah.
So for this class, what do you want us to study? Do you want us to
Memorize to be mediocre.
So for this one, yeah, just the LC. The LCR, I don't expect you to memorize it for the test, and nor do I expect you to be able to derive it for the test.
So you want us to know how to derive that?
But derive this one. Yeah. So that one's pretty good. Just an LC circuit.